Good morning, everyone. Thank you, Dr. Ramakant, for your nice introduction about me. It is my great pleasure to participate in the celebrations of National Science Day in your institute. On this wonderful event, let us brush up the basics underlying the significant discovery called Raman effect. Ask the right questions, and nature will open the doors to her secrets, said C.V. Raman, and that is what he did. In 1921, on a voyage from England to India, C.V. Raman had a question to nature. Why does the sea appear blue, whereas a glass of water is just colorless? His research culminated with him being awarded the 1930 Nobel Prize in Physics for his work on the scattering of light and for the discovery of the effect named after him. A few days before his death, on 21st November 1970, Raman spoke these words. Science can only flower out when there is an internal urge. It cannot thrive under external pressure. Sir C.V. Raman was known for his driving ambition and passion for science. He discovered Raman effect while working in the laboratory of the Indian Association for the Cultivation of Science in Kolkata. On February 28, 1928, he verified and established his discovery called Raman effect. The Nobel Prize in Physics for the year 1930 was awarded to C.V. Raman. This was the first Nobel Prize for India and Asia's first Nobel Prize in Science. Hence, the date 28 February is of great importance for Indian science and scientific community. What made him a genius? Raman wasn't just a brilliant student. He was also intensely curious about the world around him, and it was this vibrant curiosity that led him to scientific discoveries of immense significance. Moreover, he was a great experimentalist. From the year 2013, Raman effect has been designated as an international historic chemical landmark by the American Chemical Society. To commemorate and honor this event, always in the future, the National Council for Science and Technology Communication (NCSTC) asked the Indian government in the year 1986 to designate 28th of February as a National Science Day in India. India celebrated the first National Science Day on February 28, 1987. The NSD, that is the National Science Day, is celebrated with a view to spread the message about the significance of science and how it improves the daily lives of the common folk. In addition, its celebration also has the following objectives. Number one, display all activities, efforts, and achievements in the field of science. Number two, to provide opportunity those citizens of India interested in science, to foster and encourage interest in science and technology. Since 1999, the National Science Day has been celebrated keeping in mind certain specific themes. And this year, 2016, scientific issues for the development of the nation. The study of natural phenomena, that is, the scattering of light in solids, liquids, gases, by Raman and his group of scientists, has led to the development of new branch of knowledge called Raman spectroscopy. Raman spectroscopy is an increasingly popular technique in many areas, including biology and medicine. So, let us try to understand the basics underlying this great discovery. Light is an electromagnetic wave with varying electric and magnetic fields that propagate in space. These are perpendicular to each other and to the direction of propagation in space. Electromagnetic rays can be divided into parts with reference to the wavelength into gamma rays, X-rays, ultraviolet radiation, visible light, infrared radiation, microwaves, and radio waves. As you see in this picture, gamma rays have the shortest wavelength and highest frequency. The region of visible light wavelengths is from 400 nanometers, that is, you see the violet color here, to 700 nanometers, red color. In between, you can see colors blue, green, yellow, and orange. When I say light, In this context, I mean the entire range of electromagnetic spectrum and not the visible part alone. Actually, radio waves, microwaves, infrared waves, visible ultraviolet, X-rays, gamma rays refer to different energy ranges in the electromagnetic spectrum. The smallest quantity of energy is called quantum, and a beam of light is a wave-like, but it's also a stream of particles called photons, that is the light particles of light. The energy of a single photon is E, that is equal to h into nu or h into c by lambda, where E is the photon energy, lambda is the photon's wavelength, and c is the speed of light in vacuum, whereas h is the Planck's constant. The amount of energy is directly proportional to the photon's electromagnetic frequency and thus equivalently is inversely proportional to the wavelength. The higher the photon's frequency, the higher is its energy. When light falls on an object, it may be transmitted, reflected, absorbed, or scattered in different directions. Transmission of light. Transmission of light is the moving of electromagnetic waves through a material. Photons pass through the material because they don't have any sufficient energy to excite a glass electron to a higher energy level in this picture. Photons of visible light, that is with wavelengths 400 to 700 nanometers, corresponding to the colors violet, indigo, blue, green, yellow, orange, and red, simply pass through the material of this material, that is glass. Look at this transparent car, which is made up of acrylic, a substance which is transparent. So this shows off the next generation automotive safety features. The substance allows the photon to pass through unchanged. The photon doesn't interact with any electron and continues its journey until it interacts with another object. When light is reflected off the surface, the transmission can be reduced. The transmission can be stopped also when the light is absorbed by the molecule in the material. Black color is the result of complete absorption of light. This is an insect of a bright red color belonging to the mite family. When red light is reflected off its surface, all other colors get absorbed. Similarly, we can cite a number of examples here in these slides. Whenever light hits an object, some of it can be absorbed and some of it can be reflected. Deflection is one direction is called reflection. Reflected rays are responsible for creating images in mirrors, showing the color of an object and actually allowing us to see anything at all. Deflection is in all directions is called scattering. Some particles and molecules found in the atmosphere have the ability to scatter solar radiation in all directions. The sky appears blue when the atmosphere is clean without dust particles and clouds, as atmospheric gaseous molecules, namely oxygen and nitrogen, scatter the blue light. That is how the sky appears blue. Raman travelled on sea to attend Congress of Universities of British Empire at Oxford in the year 1921. A voyage to Europe in the summer of 1921 gave me the first opportunity of observing the wonderful blue opalescence of the Mediterranean Sea, said Professor C.V. Raman. He observed the blue opalescence of the Mediterranean and wondered about the origin of this beautiful phenomenon. The blue color of the sea motivated him to the extent that he could discover Raman effect. Thus, a sea journey by C.V. Raman placed India on the global science map. Raman did not accept Lord Rayleigh's explanation regarding the color of the sea. What Rayleigh said was, the color of the sea was due to the reflection of the blue sky. No, that would not be the reason, said Raman. So there must be something else. What it would be? This was Raman's new research obsession. Raman carried with him a pocket-sized spectroscope and a Nicol prism, and he made observations of the Mediterranean Sea. With a polarizing nickel quartz prism, he quenched the surface reflection of the sky on the sea surface. The intensity of the blue color of the sea was not reduced. In another experiment with a diffraction grating, he showed that the maximum spectral intensity was different for the blue sky and the blue sea. The reason the ocean is blue in color is due to the absorption and scattering of light. In water, absorption is strong in the red and weak in the blue. Thus, red light is absorbed quickly in the ocean, leaving blue. The red, yellow, and green wavelengths of sunlight are absorbed by water molecules in the ocean, and the blue gets scattered by water molecules. Raman sent two papers to the journals Nature, positing that the color of the sea was due to light scattering by the water molecules, a phenomenon he called molecular diffraction. Thus began Raman's research obsession, that was the molecular basis of light scattering. In 1923, Adolf Schmeckel predicted if light scatters off a molecule, some of the scattered light should be a different color than the incoming incident light. Raman and his students observed the frequency shift of the scattered light. Photons with energy proportional to frequency strike the molecules of a sample. Most of the encounters are elastic, and the photons are scattered with unchanged energy, that is, unchanged frequency. On some occasions, the molecule takes up energy from the photons or gives up energy to the photons, which are thereby scattered with diminished or increased energy and hence with lower or higher frequency. The frequency shifts are thus measures of the amount of energy involved in the transition between the initial and the final states of the scattering molecule. Raman showed that the frequency shift is characteristic of the molecule and independent of the frequency of the incident light. This figure is an illustration of Raman and Rayleigh scattering by a molecule. The wave showed with green color from the laser got scattered with the same wavelength green is that of Rayleigh scattering. A part of the light is shifted towards blue having a wavelength less than the incident light, and this is called anti-Stokes-Raman scattering, while the other is shifted towards red with a higher wavelength and is called Stokes-Raman scattering. This differentiated the Raman effect from fluorescence. Fluorescence strongly depends on the frequency of the incident light. Chemicals in the rocks absorb ultraviolet light and emit visible light of various colors. This process is called fluorescence. Whereas Raman effect, this is not at all dependent on the incident frequency of the incident light. It only depends upon the nature of the molecule. It is characteristic of the molecule itself. The pattern of Raman lines is characteristic of the particular molecular species, and its intensity is proportional to the number of scattering molecules in the path of the light. Thus, Raman spectra are used in qualitative and quantitative analysis. The energies corresponding to the Raman frequency shifts are found to be the energies associated with transition between different rotational and vibrational states of the scattering molecule. Most Raman work is concerned with vibrational transitions, which give larger shifts observable for gases, liquids, and solids. Raman scattering is about a million times less intense than the Rayleigh scattering. Therefore, to obtain Raman spectra, it is necessary to prevent Rayleigh scattering from overpowering the weaker Raman scattering. Figure shows the Raman spectrum of carbon tetrachloride measured using a 532 nanometer laser, indicating the Rayleigh scattering, Stokes-Raman and anti-Stokes-Raman scatterings. And this is the Raman spectrum of sulfur. In order for a vibrational transition to be Raman active, the molecule must undergo a change in the polarizability during the vibration. Polarizability refers to the ease of distorting electrons from their original position. This figure illustrates the symmetric stretching modes of the CO bonds of the carbon dioxide molecule. Since both bonds are stretched bonds and are more easily polarizable, the overall molecular polarizability changes and the symmetric stretch is Raman active. But this symmetric stretch of carbon dioxide is not IR active because there is no change in the net molecular dipole. In case of asymmetric stretch of carbon dioxide, the change in polarizability of the longer bond is exactly offset by the change in the shorter bond such that the overall polarizability of the molecule does not change. Therefore, the asymmetric stretch is not Raman active. The asymmetric stretch of carbon dioxide, on the other hand, is IR active because there is a change in the net molecular dipole. Thus, in short, Raman spectrum is based on Raman scattering, a phenomenon in which incident photons lose or gain energy via interactions with vibrating molecules in a sample. All this scientific research needed independent thinking and hard work, and not equipment. The research work which brought me the Nobel Prize did not cost more than 300 rupees. A table drawer can hold all my research equipment and equipments, said Raman. In India, a research scholar working with Raman was using a X-ray tube of 1 kilowatt power. And he came to know that in England, a research scholar working on the same problem was using 5 kilowatt power X-ray tube. This was very much worrying him. Having known about this, Raman said like this: there is a simple solution. Use a 10 kilowatt brain on the problem. Thus, Raman advised his student to use 10 kilowatt brain instead of worrying about the available equipment. Raman spectroscopy is an increasingly popular technique in many areas. This is a light scattering technique whereby a molecule scatters incident light from a high intensity laser light source. A Raman spectrum features a number of peaks showing the intensity and wavelength positions of the Raman scattered light. Each peak corresponds to a specific molecular bond vibration, including individual bonds such as C single bond C, C double bond C, N, O, CH, etc. Typically, a Raman spectrum is a distinct chemical fingerprint for a particular molecule or material and can be used to very quickly identify the material or distinguish it from others. Raman spectral libraries are often used for identification of a material based on its Raman spectrum. Libraries containing thousands of spectra are rapidly searched to find a match with the spectrum of the analyte. Typical examples where Raman spectroscopy is used today include some of them like this: art and archaeology, carbon materials, chemistry, geology, life sciences, pharmaceuticals, semiconductors, etc. Sir C.V. Raman ఈ నోబెల్ పురస్కారాన్ని అందుకున్న తర్వాత వాళ్ళ ఊర్లో, వాళ్ళ పల్లెటూరులో వాళ్ళ మేనత్తగారిని కలవటానికి వెళ్ళాట. వెళ్తే ఈయన చూసిన వెంటనే ఆవిడ అడిగితే, ఏమిట్రా అబ్బి, ఏమిట్రా కనుగొన్నావు? ఊరికే పేపర్ల నిండా దుమ్మెత్తిపోస్తున్నారు, రేడియో విప్పితే నీ సంగతే చెప్తున్నారు, ఏం కనుగొన్నావురా అంత పెద్ద విషయం అందిట. అంటే సరే, ఆయన రామన్ గారు ఆవిడికి తను కనుగొన్నటువంటి విషయం ఏమిటో చాలా సరళమైనటువంటి పదాలతోటి బోధపరిచేట. ఆవిడంతా విని అందట, ఇంతేసట, దీనికే అంత పెద్ద బహుమానం ఇచ్చారా, నాకు చాలా ఆశ్చర్యంగా ఉంది సుమా అందిట. అంటే ఈ రామన్ ఎఫెక్ట్ కనుగొనడం కానీ, ఈ రామన్ స్పెక్ట్రోస్కోపీ కానీ, ఇంత అప్లికేషన్స్ అన్వయాలు ఉన్నటువంటి రామన్ స్పెక్ట్రోస్కోపీ కానీ ఆవిడికి ఏమనిపించిందంటే, ఇట్స్ ఎ సింపుల్ థింగ్ అనిపించింది. ఆఫ్టర్ ఆల్ ఇట్స్ ఎ సింపుల్ థింగ్. I don't know, it was so simple. I am surprised that such a simple thing should have merited international recognition అందట ఆవిడ, the old lady. అది సంగతి. థ్యాంక్ యూ ఆల్.